Welcome to The Explainer. Today we're going to dive into a really cool engineering secret from this technical guide, a system that lets architects build these huge, wide-open rooms that look like they're held up by nothing at all.
All right, let's kick things off with a challenge, one that seems to totally defy gravity. Picture a massive library or a big exhibition hall. The last thing you want are columns everywhere, right? They just get in the way. So how in the world do you hold up the roof?
Well, the answer is this really elegant system called paneled beams. Instead of using a couple of giant, bulky beams, the idea is to use a whole grid of smaller beams that cross over each other. They all work together, turning the entire ceiling into its own support structure.
Okay, so let's get into it. Here's the game plan for how we're going to break this all down, step by step, starting from the top.
All right, first up, let's talk about why this system is such a perfect solution for creating those huge open-plan spaces.
Yeah, we're not talking about your average living room here. Paneled beams are built for big jobs. We're talking spaces large enough for a university lecture hall all the way up to a massive convention center. And get this, not a single column in sight.
You know, the idea behind it is actually pretty simple, but it's totally brilliant. You lay out this grid of beams, and it basically takes one huge complicated structural problem and chops it up into a bunch of smaller, much more manageable pieces. Each little panel is now supported on all four of its sides, which makes the whole thing incredibly strong and efficient.
Okay, so how do you actually design one of these things? Well, the whole process starts from the top and works its way down, beginning with the concrete slab itself. Now, designing the slab, it's a super methodical process, exactly how an engineer would tackle it. You start with a good guess, an educated guess, and then you calculate your way to the final answer.
First things first, you need a starting point, right? So we have to guess the slab's thickness. And luckily, the guide gives us a great little rule of thumb for this. Just take the shorter side of one of those panels and divide it by 40 or 45. Easy.
Okay, with our thickness assumed, next up is figuring out all the forces pushing down on that slab. And that includes everything: the weight of the concrete itself, any flooring on top, and what engineers call the live load, which is basically us, furniture, you name it.
All right, so we've got the total weight, but here's where it gets really interesting. How does all that weight get shared between the beams? It's definitely not a 50-50 split, and the reason why is pretty cool.
It's not even close to an even split. This gets at a core principle in engineering. Load always follows the stiffest path. Just think about it. Try bending a short ruler versus a long one. The short one is way stiffer, right? So it fights back more, and because of that, it ends up taking way more of the load.
So to get the exact numbers, engineers have this tool called Grashoff's method. And the whole thing, the entire calculation, boils down to just one key number, R, the aspect ratio. That's simply the long side of the panel divided by the short side. That's it.
And this slide just illustrates that point perfectly. Look at these formulas. Alpha, that's the percentage of load going in the short direction, has R to the power of 4 in it. So as the panel gets longer and more rectangular, R gets bigger, and that R to the fourth term just explodes. Alpha gets super close to 100%, meaning almost all the load goes that way. And beta? Well, it gets whatever's left over.
So we've got the slab figured out. We know how it's handling the load. Now it's time to design the beams that are holding the whole thing up. And that whole alpha and beta thing we just talked about, that's the key to this whole next step.
You'll see the process for the beams is a lot like the slab design. We assume some dimensions, we calculate the load, and then we distribute it. But there's a really clever trick here for calculating the load that makes everything way, way simpler.
See, instead of going through the headache of calculating the exact load on every single little piece of beam, the method does something brilliant. It creates an average weight for the entire system. It's like it mathematically smears the weight of the slab and all the beams perfectly evenly across the whole floor. Super clever.
Okay, now for the steel inside the concrete, the rebar. This is crucial. It's laid out in 2 layers. The main, bottom layer, goes in the shorter direction, because that's where that big alpha load is. The secondary layer then goes on top of that, running the other way. Now, because that top layer sits a little higher, its effective depth, what we call D, is a bit smaller. It sounds like a tiny detail, but trust me, getting that right is absolutely critical for the strength calculations.
All right, let's pull back and bring it all together. We're going to summarize the core ideas that make this whole elegant system tick. So what are the big takeaways here? First, always design from the top down. Slab first, then beams. Second, that aspect ratio, R, is everything. It tells you exactly where the load is going. And that leads to the big one. Shorter spans are stiffer, so they carry more load.
That's why you always put your main steel in that short direction. And finally, don't forget that the 2 layers of steel have different effective depths. Get those rules down and you've got the blueprint.
You know, when you step back, the beauty of this whole system is just how efficient it is. It takes what seems like an impossibly complex problem, spanning a massive room with no columns, and it just breaks it down into a simple grid of problems you can actually solve.
And that's our explainer. But this idea, this fundamental principle that stiffness attracts load, it's not just for concrete floors. You see it everywhere in engineering, from the wings of an airplane to the frame of a bicycle. Which leaves us with a final thought to chew on.